Hi students, welcome to the second part of this video. Now in this video we will learn about the ES reactions, electrophilic aromatic substitution reactions. We know that aromatic compounds do not undergo the addition reactions, they follow the substitution reactions, right? In an alkene we know that there is a double bond, and the most common reaction for an alkene is that it undergoes addition reactions, right? We know there is a sigma bond and a pi bond, and the pi bond can easily break down, and what you get the addition compound, right? So if electrophile attacks on the one carbon, nucleophile attacks on the second carbon. So this is the most common reaction for the alkenes. But that kind of a reaction is not possible for the aromatic compounds, because the most common reaction with the aromatic compounds is substitution rather than the addition, right? So they do not follow the addition, rather they undergo the substitution reaction. You can replace the hydrogen from the aromatic ring, from the benzene ring, as an H positive by any other electrophile. So that's why the most common reaction here is electrophilic aromatic substitution reactions. But why the aromatic compounds do not undergo the addition reaction? Why they don't follow generally the addition reactions? Because aromatic compounds, we know, are more stable compounds, right? If they undergo the addition reaction, they will lose the aromaticity, correct? So aromatic compounds will lose the aromaticity if they undergo addition reactions. That's why they do not follow the addition reactions, rather they undergo the electrophilic aromatic substitution reactions. Now what are the different types of ES reactions, right? The five most important ES reactions, the electrophilic aromatic substitution reactions that we will discuss in this video are: number one is the halogenation, right? The second is nitration, okay, the sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation, right? These are the five different types of ES reactions that we will discuss. Now let's start with the halogenation. The first one, the halogenation. Halogenation means if you take a aromatic ring, a benzene ring, and you react it with any halogen molecule like the chlorine molecule, Cl2 molecule, and then what you will get? You get the chlorobenzene. You can replace the hydrogen from the aromatic ring and you get the chlorobenzene. The hydrogen is replaced from the aromatic ring by the chlorine, and you also get the HCl. But normally we carry out the reaction in presence of a Lewis acid, a catalyst, right? The important catalyst, right? So the Lewis acid AlCl3. You can use any other you can use any other Lewis acid as a catalyst here, right? And in this reaction we find that Cl positive is actually first generated from the chlorine molecule, and that Cl positive replaces the hydrogen from the ring and forms the chlorobenzene. This is an electrophilic substitution reaction, because hydrogen gets replaced as H plus by the Cl plus. One electrophile replacing another electrophile. But now let's see how this reaction actually occurs, right? What are the steps in this reaction, correct? So the first, when you look at the reaction, the first thing that comes to our mind is that we need to generate an electrophile. We need to first generate the Cl positive from the chlorine molecule, correct? So that's why when we write down the mechanism of reaction, the first step in the halogenation is basically generation of an electrophile. So let's write down the mechanism of this reaction, okay? So the first step here is in this halogenation is that the chlorine molecule, right? The chlorine molecule, it reacts first with the AlCl3. We know the Lewis acid is the one which can accept electron pair, okay? And aluminium can accept electron pair. Chlorine here, it has the lone pair of electrons, okay? It has a lone pair of electrons, and what you actually get, the Cl, this electron pair, it forms a coordinate bond with the chlorine, and then this bond breaks down here, okay? The chlorine, it forms the bond with the aluminium, right? And the chlorine comes off here at the Cl negative, and what you get? You get AlCl4 negative now, right? Because AlCl3 is a Lewis acid, right? It's an electron pair acceptor, right? And with the chlorine molecule, it forms a bond with it, and the chlorine comes off. Cl negative comes off from the Cl2, and you also get the Cl positive, right? This chlorine is now the Cl positive, right? So you get the AlCl4 negative and the Cl positive. This is the first step, right? So the first step is generation of an electrophile, correct? So we have to generate an electrophile. This is the first step in the halogenation. In any electrophilic substitution reaction, actually the first step is formation of an electrophile, or you can say the generation of an electrophile, correct? So this is the first step. And the second step, in the second step there is an attack of an electrophile, right, of the on the benzene ring, correct? So the same electrophile will attack now, okay? Attack of the electrophile. This is the second step of the mechanism, right? Attack of the electrophile. The electrophile attacks on the benzene ring, on the aromatic ring, and it forms a bond. Actually, if you see here, if you have double bond there, now electrophile Cl positive, it forms a bond and uses the pi electrons to form a bond here with this one, right? So you get a molecule like this, and you get an intermediate like this, right? You got the Cl with this chlorine and this carbon. So for example, it forms a bond, okay? If the chlorine forms a bond with the carbon, right, and ortho position here, it gets a positive charge, right? The same carbon, if you look at, then this can undergo the resonance, this positive charge can undergo the resonance, but I'll write down here the final product. When the chlorine, when the electrophile attacks on the benzene ring, you get an intermediate, a carbon get an intermediate. Then the same carbon, while the chlorine is attached, okay, it releases the hydrogen as H positive, as H positive. Hydrogen is lost here as H plus, and the electron pair goes down inside the ring, and it forms a double bond there, right? Now when this goes down, and you get a double bond over here, and you get the chlorine, and what else is there? H plus, right? H plus. So we got the chlorobenzene. This is the product that we need. Second step is attack of electrophile. When the electrophile is formed here, that attacks on the ring and forms this intermediate, right? And intermediate, it releases the hydrogen as H plus and forms the chlorobenzene plus H plus ion. And then see that we know the AlCl3 is a catalyst, and we have to regenerate the catalyst back, correct? And then the third step is the regeneration of a catalyst. And how is that possible? The AlCl4 negative here, okay, in the first step that was formed, AlCl4 negative, again now it reacts with the H plus ion over here, and it forms the HCl plus AlCl3 negative, AlCl3. So this is the catalyst back. So overall the reaction is that the chlorine molecule, Cl2 molecule, reacts with the benzene and forms the chlorobenzene plus HCl. So if you look at the reaction, if you look at the different steps in the mechanism of the reaction, the first step is attack of electrophile. The first step is generation of an electrophile. When the electrophile is formed. Second step is the same electrophile attacks on the ring, and you get the product. The third step, you regenerate your catalyst back. Okay. So the overall reaction is, what is the overall reaction? The overall reaction is that the benzene molecule reacts with the chlorine in presence of AlCl3, has a Lewis acid as a catalyst, right? Okay, and what you get the chlorobenzene plus you get the HCl, right? This is the reaction. This is the halogenation. You can do it with any other electrophile, right? You can do it with any other halogen molecule. Now let's take another example. First thing is halogenation, right? This is the 1-ES reaction. Now let's discuss about the nitration. What the nitration is? Nitration is if you take the benzene, react the benzene with the nitric acid, HNO3, right? HNO3, and you react it with in presence of a catalyst. The H2SO4 we use as a dilute H2SO4 we use as a catalyst, sulfuric acid. Okay, so this is a catalyst here, and what you get? You get the nitrobenzene, because the electrophile that we generate from the nitric acid is NO2 plus, okay, and that NO2 plus replaces the hydrogen from the benzene ring, and what you get? You get a nitrobenzene. You get the nitrobenzene, okay, plus you get the water there. This is the overall reaction, right? So nitration is addition, reaction of the benzene with the nitric acid, right? And you get the nitrobenzene. The electrophile is NO2 plus. So if you again write down the mechanism of the reaction, correct? So that will be the same thing, the same steps. Number one step will be formation of electrophile. How we generate the NO2 plus from the benzene ring, from the nitric acid, and then the second step is the attack of that NO2 plus, the attack of the electrophile on the benzene ring, correct? It will replace the hydrogen from the benzene ring, correct? So let's write down the mechanism of this reaction, how the reaction actually occurs. So first step, right? The first step, as usual in any electrophilic aromatic substitution, is that we have to generate the electrophile. So we can say the first step is generation of, right? The first step is the generation of electrophile. Okay, here the electrophile is NO2 plus, right? NO2 plus. So we have to generate the electrophile, and that is the very important step. We'll learn how we get this. If you look at the nitric acid, the nitric acid is like this, okay? And nitric acid, in presence of the catalyst H2SO4, right? H2SO4 basically it provides the H plus sign, okay? The H plus sign that attacks on the OH of this one, right? And you get an intermediate like this, okay? And now what do you get? You get oxygen, H, and when there is protonation, right? When there is protonation on this OH group, so you get an intermediate like this, correct? So oxygen with the positive charge. So coordinate, a bond is formed with a lone pair and the H plus sign, and then this comes off, so you get the water, right? So you get the water here, this one forms the water, and then from this one what you get? You get the NO2 plus. Nitrogen, it loses the electron pair, so you get the NO2 plus. This is the electrophile that is actually formed in the first step, right? So this H2SO4, this NO2 plus electrophile is generated from the nitric acid by the action of a catalyst, right? The catalyst we take is H2SO4, because it is the H2SO4, the sulfuric acid, that provides the H plus sign to the nitric acid, and you generate the NO2 plus. The second step, the same thing like we discussed in the previous reaction, that is the attack of the electrophile, right? So the benzene ring will be under the attack of this electrophile. So the benzene ring, suppose it has a hydrogen here, okay, the NO2 plus, okay, it attacks on the same ring, and again you get the same intermediate, correct? Like in the previous example we have discussed, you get intermediate like this. You have a hydrogen and you have a NO2 plus. At this position you have a positive charge, and then the hydrogen comes off as H plus. The electron pair goes inside the ring, and what you get? You get the nitrobenzene, right? So you get the H plus sign. And the third step, again the same thing, to regenerate back this the catalyst, right? Because from the H2SO4 what we got the H plus sign, this H plus, again you can say it reacts with the HSO4 4 negative there, right? And it forms the H2SO4, because we use the H2SO4 to provide the proton initially that forms the water, and we have to regenerate the H2SO4 back, correct? So that's why we get this one. So overall reaction is what? Overall reaction is that the benzene reacts with the nitric acid, HNO3, in presence of the sulfuric acid, right? Dilute sulfuric acid, and you get the nitrobenzene, right? Plus you get the water, H2O. Actually the H from the benzene reacts with the OH from the nitric acid and forms the water, and you get the nitrobenzene. This is the overall reaction, correct? This is the nitration.